All right, mathletes, here's 4.1, composition of functions. So our purpose of this is to form and evaluate composition of functions. What is a composition of function? Well, a lot of times it's going to be written in two formats. One is here where you have the open circle, and it's read as f of g of x. It's also interpreted like this, where it's f parentheses g of x, where g of x is the input into f of x. Okay, so that function is actually the input, where you would typically just see f of x here. The entire x, your input is a function. So it's the input of one function depends on the output of another function. We call this a composition of functions. So let's look at some examples here. Okay, so if I want to evaluate each of the following expressions, I want to find f of g of negative 5. So for these, I want to work for the inside out. So my g of negative 5, well, g negative 5 is going to be equal to 1 minus 2 times negative 5. This is equal to 1 plus 10, which is equal to 11. Well, now I do a substitution, so then I get f of 11. Well, now I evaluate that. So I do the square root. Where I had an x before, I place an 11 minus 2, and I get the square root of 9, which is equal to 3. Okay, so now if I want to do g of f of positive 2, again, I'm going to work from the inside out, f2. So f at 2 is equal to the square root of 2 minus 2, which is 0. So then I do a substitution where f of 2 was equal to 0. I substitute that into here, and I have g of 0 is equal to 1 minus 2 times 0, which is equal to 1. Okay, so some other examples. So here, notice the notation is different, but this is still being interpreted the same. It's f of g of negative 3. So I want to evaluate g at negative 3 first. So I get this is equal to 1 minus 2 times negative 3, which is equal to 1 plus 6, which is equal to 7. Then I evaluate f at 7, and I do square root is equal to 7 minus 2, which is equal to the square root of 5. Okay, now g of 2, so I can send things through a function twice. So g of 2 is equal to 1 minus 2 times 2, which is equal to 1 minus 4, which is equal to negative 3. Now I plug it through my output of that one is now my input of g again, so g of negative 3, this just came there, is equal to 1 minus 2 times negative 3. Well, this is equal to 1 plus 6, which is equal to 7. Okay. All right, let's look at another example. So now we want to use the same functions, and we just want to write these in terms of x. So our output, notice we don't have any values here, so our output, our solutions is going to be an equation. It's going to be an expression. So I usually like to write it like this. So I get f of g of x. And I work from the inside out. Well, what's g of x? Well, g of x is here, but I'm going to substitute in the right side. So then I get f of 1 minus 2x. Well, what this says, wherever I see an x here, I put in over here. Well, this is my input, so I need to make sure that that is the square root of, well, again, I have 1 minus 2x. That was representing that piece. and then I have a minus 2 for that function. So that was my entire input. So I just want to usually simplify them out if I can. So I get a square root of minus 1 minus 2x is equal to f of g. Okay. Here I can do g of f, so I'm going to again write it g of f of x. Well, f of x I can substitute in as a square root of x minus 2. Well, now I'm going to rewrite g of square root of x minus 2. And everywhere I see an x in the g equation, I get 1 minus 2. Well, this x is now being represented by my input. So in here, I got to put the square root of x minus 2. Can clean this up a little bit, and I get 1 minus 2 square roots of x minus 2. Again, g of g, I'm going to have g of x. And then I have g of, well, what's g of x? It's 1 minus 2x. And, well, if I plug that in for my x's, I get 1 minus 2 here. Needs to be represented here. So that's 1 minus 2x. I simplify this, I get 1 minus 2 plus 4x, which is equal to negative 1 plus 4x. So that's g of g, my function. Notice all three of these are functions upon themselves. They are involving an equation. They still have x's in their solution. All right. So we need to be able to talk about domain of composite functions. The domain of f of g is a set of all numbers in x in the domain of g, such that g of x is in the domain of f. Okay, so it's valuable to look at each function individually. So for f of x, square root of x minus 2, well, we know that it's going to be for all real x's, and for square roots, I know that that's going to eliminate things. I can't have this to be negative, so x minus 2 has to be greater than or equal to 0, or otherwise x has to be greater than or equal to 2. So such that x is greater than or equal to 2. G of x is just a polynomial, so it's for all real x values. Okay, so if I want to find the domain of each composite function of number 2, remember this is what I got on my previous example of f of g of x. I don't necessarily have to evaluate that to find my domain, but I have to think, all right, for g of x, I cannot have, for g, I can have all real numbers, so I don't have any issues there. But my issue comes from my f of x function, so the second piece here. Well, that f of x function has this domain restriction of x has to be greater than or equal to 2. Well, my input, my x, is coming from this function. So what I need to do is I need to take the domain of my second one, which is for x greater than or equal to 2, and I got to make sure that I can't let this value, which this is my input, is coming from this function. So I go ahead and do a substitution here. So I do 1 minus 2x is greater than 2. So this is my function g of x, the first part. I set that equal, or I set that in place of x into my domain here for my f. If I solve this out, I'm going to go ahead and subtract 1 from both sides, get negative 2x is greater than or equal to 1. Divide by negative 2, so I got to flip my sign. So x has to be less than negative 1/2. So it's for all real x's, such that x has to be less than or equal to negative 1/2. When you look at this function here, it should make sense. Okay? If I plug in x being equal to 0 here, I get the square root of negative 1, and that doesn't work. So I got to understand that, well, if I plug in x being negative 1/2, this goes to the, a plus 1, negative 1 plus 1. This is going to be the square root of 0, and that works. I can have values smaller than that because of this negative, but if I have values larger than that, let's say 2, right, that's just going to be multiplied by a negative. I get larger and larger, and I can't have a large negative number in my radical. Okay, so that would be my domain for f of g of x. Okay, well, for f, so for part B, so f, I have an issue with my domain. My domain for f has to be, x has to be greater than or equal to 2. Well, for my g function, I don't have any restrictions upon my domain, so this is just carried over. We can look at our function here, and that makes sense that we cannot have values less than that. So again, this carries over as the same domain as f, such that x is greater than or equal to 2. Now g of g, remember this is negative 1 plus 4x. Again, if it's for all reals for my input and my output, my domain, then that's going to carry over, and it's up for all real x's as well. All right, let's look at another example. So sometimes we're not going to be given functions as equations, but just given graphs of functions, and we should be able to evaluate these as well. This is a great skill to carry over into calculus when we start talking about integral graphs and derivative graphs. So again, just evaluate it from the inside out. So first I want to look at g of 1. Well, g of 1, here's my function that's the graph that's defining my g. So my x value at 1, I can see g is 2. So that simplifies my graph equation. Now this, I substitute g at 1 is 2. 1 is 2, so I do that substitution. Well, what's f of 2? Well, f is my blue function up here, so I go where my blue function has a 2, so my output became my input, and my input at 2, so right here I can see that this is 2, 4, 6. So f at 2 is equal to 6. Okay? So another example here is now f at 0. So this is my blue function. So I'm going to go to where my x is 0, and my output there, my y value, is 5. So then I'm going to evaluate g at 5. Okay, so my output now becomes my input at g. So for g is my red function. So I go over to an x value being 5, and I can see that g is equal to 2. Okay, so we can do that graphically as well. Example 4 here, again, it's another domain question of the function f of g of find the domain. Okay, so first I'm going to state the domain for f. Okay, so the domain for f, again, rational functions, I can't have that equal to 0, so it's for all real x's such that x cannot be equal to -3. Okay, g of x, the domain of g, domain for g is, again, I can't have this domain being equal to 0, so it's for all real x's such that x cannot be equal to 0. All right, so for f of g of x, I want to think of g. Okay, so my issues at g are 0. So for f of g of x, the domain, that's going to carry over. So it's going to be for all real x's such that x cannot be equal to 0. So that carries over for our g. Okay, for f, our inputs for f come from g. So for f, I cannot have things equal to -3. That means I cannot get an output from my g of x to be -3. So -3 cannot be equal to my g of x, which is 2 over x. Well, when does that happen? So if I solve this out, I solve that x is equal to -2/3. Well, actually, we're saying when they can't be equal to that. So not only can it not be equal to 0, but it can't also be equal to -2/3. Okay. Now for g of g. So g, I have 2 over x. And so the first one, again, just from my first input, I know it's going to be for g of g, the domain is going to be for all real x's, such that x can't be equal to 0. The other one could come from, well, I don't want 0 to be the input into my g here. Well, 0 cannot be equal to 2 over x. Well, that can never happen because our numerator is 2, and if x was 0, where it's undefined, so we don't get any other restrictions upon our domain for that one. So this just remains as that. Last piece here is just to show that the inverse of a function is equal to x, and also going the other way. So f of g of x, so I'm going to do f. G of x is 1/3 of 4 minus x. So if I evaluate this, I'm going to do my function f. So I do 4 minus 3. Well, my input is g of x. And now as I simplify this, I hope that it's equal to x. So -3 multiplied through to this, I'm going to get 4. And then that's going to be minus 4 minus x. And then I get 4 minus 4 plus x, which is equal to x. So we're good on showing that this is equal to x. Now we want to show that this is equal to x as well. So g of, well, what's f of x? That's 4 minus 3 of x. So g is going to be 1/3. 4 minus, well, my input for g now is my f of x. So that's going to be 4 minus 3x. In the quantity, make sure I remember my parentheses here, because this negative is going to have to distribute through. So simplify, I get 1/3 of 4. Now let's distribute that negative. Minus 4 plus 3x. Simplify within my, those cancel out, and I get 1/3 of 3x, which is equal to x. So I've now shown that f of g of x is equal to x, and g of f of x is equal to x. So they're also equal to each other. That concludes our notes on 4.1. Go ahead and highlight any questions you have and bring them to class tomorrow.